Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. It's a series of lectures in computer architecture. So, we have been looking at how different arithmetic operations are performed in a computer. So, we have looked at integer operations and we have also taken a look at an introduction as such to floating point representation. So, we now need to be looking at how these different operations are carried out on floating point numbers. So, that will be today's topic, how we do different operations on floating point numbers and what are the basics that are required for doing those operations. So, remember our representation of floating point numbers. So, we have a bit associate that is allocated for the sign of the mantissa, and then you have a set of bits allocated for the exponent and a set of bits allocated for the fractional mantissa. So, remember whenever we talk of floating point numbers, we talk about a mantissa, an exponent and a sign bit. That is, I may have a number like let me give you a decimal example again. So, minus 1.2 into 10 to the power of 23. So, if I do that, minus will be the sign bit, 1.2 will be my mantissa and 10 to the power of 26. So, 23 would be my exponent. So, here the base that we are looking at is 10, but when you are looking at binary numbers, our base implied base as such will be 2. So, the 2 need not be represented. So, we just need to represent the exponent, the sign bit and the mantissa. So, in this example where I am using 32 bits for representation, out of the 32 bits we are using 1 bit for the sign bit, 7 bits for the exponent and 24 bits for the mantissa. When we deal with these kind of numbers, we often find that when we are talking about floating point numbers, there is a concept called normalization that is normally used. Now, let us understand what we mean by this normalization. So, let us take this number for instance, x equal to, this is I am just taking a decimal example, 0.000405678 into 10 to the power of 12. If I am given only 7 significant digits to represent the number, which means I can't have more than 7 digits in this mantissa portion, this number will be truncated like this, it will be represented like this, it will be 0004056, assuming that I am not doing any rounding off. So, this will be represented just as 0004056 into 10 to the power of 12. But given that I have actually 3 more digits, these 3 digits are 000, if I adjust this exponent, then you can see that I can actually represent 4056781 fully in this significant digits that are available to me. Okay, so because you can see that the same number can be represented as 0.4056781 into 10 to the power of, remember that if I shift this to accommodate for these 3 zeros here, I can write this as 0.4056781 into 10 to the power of 9. So, if you write it like that, then you can see that the same number, this number that we had here, right, with all the significant digits that we want in place, can be represented using just these same 7 slots that are available to you. Okay. So, what do we do here? All we are doing is, because you remember the 0.04 into 10 to the power of 12, if I just take 0.04 into 10 to the power of 12, okay, and I write it as 0.4, I can write it as 0.4 into 10 to the power of 11. Okay. So, this is, it would be the same thing. So, if you can specify it like this, so that is what we are doing here. So, now we have 3 positions here. So, 0.004 into 10 to the power of 12 now will become 0.4 into 10 to the power of 9. Okay. So, that is what we are doing here. So, if I do this, what I am actually doing is, when there are leading zeros in my representation, I can do away with those leading zeros and represent more significant digits in the available slots, and by adjusting this exponent appropriately. Okay. So, how do we adjust the exponent? All we do is, you decrease this exponent by 1 for every left shift of the number that we are doing here. That is, you had 0.004056. So, for 1 left shift, this will become 10 to the power of 11. If you do 2 left shifts, it will become 10 to the power of 10. Since we did 3 left shifts here, it will become 10 to the power of 9. Okay. So, this is how you would be representing the number. I mean, you are familiar with this, and this is something that we will do with respect to our binary representation as well. When we do this, we say that the number has been normalized, that the representation is in a normalized representation. Okay. So, if you look at the binary number that we have here, say let us say we have this number here 000110100. Okay. This is multiplied by 2 to the power of 8, let us say. Again you can see we are assuming a binary point here to the left. So, 0.00011. So I can do again left shift of 3 here and write this number as 0.110100010. Now where did all these extra bits come from? These are the extra bits that are actually available. If it was a large number that we had here, and these are the bits that are here available to the right here, these numbers, 2 out of these 5 can be accommodated within whatever I have here. So your number now becomes 1101001001. Okay, so there are only two bits out of this. Out of the 5 here, only 2 have not been accommodated in this representation. Up to 3 out of these I can include in this representation, because I have got rid of the 3 leading zeros and instead I have brought in 3 numbers from here. Remember that you have of course adjusted your exponent appropriately. So this simple method of making sure that your most significant bit here is a 1, therefore this will make sure that your representation can now accommodate more number of significant digits. So that is what we are trying to do with normalization. When we are dealing with binary numbers, so you can see that the normalized number will always look like this. It will have 0.1 followed by whatever you have here. Okay, so there is 1 in the most significant bit position. If it is there, we say that the number is in the normalized representation. Okay, this is what we remember. So when you have the numbers in normalized representation, so you can see what will be the range of numbers that we can accommodate in this. So because every number must be normalized, it means it will always start with 0.1 something. Okay, so what is the smallest number that we can have here will be 0.1 followed by all zeros here. Okay, and the largest number will be 0.1 followed by all ones here. So the range of numbers that we can represent therefore will become 0.5 into 2 to the power of minus 64, if I am assuming that I am using that same 7 bits for the exponent portion. Okay, so it will become 0.5 into 2 to the power of minus 64 all the way up to the value which is less than 1 into 2 to the power of 63. 0.5 into 2 to the power of minus 64 is less than or equal to modulo x less, and which is less than 1 into 2 power 63. So the maximum number that I can have will be less than this value, and the smallest number I can have will be 0.5 into 2 to the power of minus 64. Of course, both can be a negative number or a positive number. So which is why we say magnitude of x is this. So the magnitude ranges between these two numbers. This is the range of numbers that we can do with our 32-bit representation. Now when we do this representation using 32-bit this kind of a normalization technique, there are 2 other problems that we could run into. One is called as an underflow and one is called as an overflow. So let's look at what these 2 terms mean. It's very simple to understand. Look at what we are doing for normalizing any number. So do until the MSB of mantissa becomes equal to 1, you shift the mantissa left or right. Okay, so you will shift it left, which means that you will decrement the exponent by 1. Okay, this is what we are doing for normalizing a number. Look at what happens when you apply it to a particular number that we have here. Suppose you have this number here 0.000111000 some number into 2 to the power of minus 62. Note this minus 62, this is important here. Okay, minus 62 is what you have here. Now if I do normalization on this number, what am I going to do? I am going to get rid of these 3 zeros. Okay, so I am going to left shift by 3 positions. If I left shift by 3 positions, the number will become 0.111001111 whatever into 2 to the power of, what will happen to my exponent? Exponent now will have to be decremented by 3. So minus 62 minus 3, it will become minus 65. Minus 62 minus 3 becomes minus 65. Now this is the number that I now have to represent after doing the normalization. But now the question is, can I represent this number in my floating point representation or not? If you look at it, you will see that, remember when we have only 7 bits in the exponent, right? So what is it? We can go only from 2 power 63 to 2 power 64. Okay, 2 power you can represent only up to 2 to the power of 63. So the moment you go to 2 power 64, you have a problem of not being able to represent that number. Okay, so whereas now what is the number that we have? We have got a minus 65 that needs to be represented. See, from minus 63 all the way to 64 you can go. So now minus 62 could have been represented, but minus 64, minus 65 if I come to, I will not be able to represent those numbers. So now the moment I do the normalization, you will find that you cannot represent that number using the exponent value that is available to you. So now it goes less than the minimum value that you can represent. So we call it as an underflow. Okay. So the same thing will happen if you do the same kind of normalization with respect to a number which exceeds the maximum value that you can represent using the exponent. Okay. So suppose you have a number like this. Suppose we had 1.00111000 into 2 to the power of 63. Now if I were to normalize this number, remember I can't have any decimal position here, right? So I will have to shift this right. So if I shift this right, what will happen? I will write it as 0.100111 whatever into 2 to the power of 64. Now remember that 64 cannot be represented using your 7-bit exponent that you have. Okay. So what will happen now, since you can't represent 64, we say that we have got an overflow in this case. So an underflow and an overflow, these are two things that can happen when you are doing the normalization. This happens because when you do the normalization, you are changing the value of the exponent. You are either adding some value to it or subtracting some value from it, and that added value or subtracted value, if it cannot be represented within the available exponent space that you have, if it is not within the range of representable exponents, then we say that we have an underflow or an overflow in the case of floating point numbers. Okay. So even for any other operation, when you do any operation on floating point numbers and you find that you are not able to represent it within that range, that is, if it becomes less than if the number is less than what you can represent within the range, we call it as an underflow. And similarly, if the number is greater than what you can represent within that range, we call it as an overflow. And this underflow overflow we actually capture with respect to the exponent bit positions. Okay, that is how we do it. Now there is another concept that we need to understand when we talk about floating point numbers, which is that of excess notation. Okay. Now this excess notation is something that you would have studied about when you talked about digital techniques, and when you started understanding principles of digital. Okay. So when we talk about digital numbers, representation of numbers using binary representation of digital numbers and so on, we talk about something called an excess 3 representation. So you will have a number, you will always represent it as 3 more than whatever value you have. So if you have 0000 to be represented, you will actually represent it as 0001, 0011. This 0 will be represented as 3, 1 will be represented as 4 and so on. We refer to this as an excess 3 representation. You may be familiar with this back from your digital days. Now this idea of an excess representation is again used when we deal with exponents in the case of floating point numbers. So let us look at how that is done. Now look at what we had. With 7 bits we saw that we can go from minus 64 to plus 63, right. This was our range that we had. With the 2's complement representation, you can go from minus 64 to plus 63. Now when we do this, you can see that in the exponents we have to deal with both negative numbers and positive numbers. That is why we are going for 2's complement representation. Now one idea that we can use here is you represent the exponent using what we call as this excess 64 representation. So the same excess notation that we talked about, okay, instead of excess 3 or some small number like that, here we use an excess 64 representation. So now what will happen is I will have my new exponent, okay, which I am calling as E dash, in the excess notation represented as whatever was the true value plus a value of 64. Let me say I had 1 as the original value, now it will be represented as 65 will be my value of E dash. Okay. So in general, any excess p coding is represented as E dash is equal to E true plus p, okay, any p, whatever be the value of p. In this case, the advantage of choosing an excess 64 representation is that minus 64 you can see will become minus 64 plus 64, it will become 0. 0 will be represented as 64 and 63 will be represented as 127. Okay. So what happens now? All our exponent values become positive numbers. So if all the numbers become positive, now what the benefit that we get out of this is that it is very easy to compare the relative sizes of two floating point numbers, because all of them are positive numbers. It is easy to identify whether which exponent is greater than other exponent and so on. So to ease computation, we go in for this excess notation. So we will take a short break now and come back and look at how different operations are performed using this floating point numbers. Welcome back after the break. So we just looked at how normalization is performed in floating point numbers, and also we looked at how the excess notation is used to represent the exponents. Okay. So we look at a few other standards that are used for representing floating point numbers, and then quickly go into the different operations. Okay. So when we talk of standards for representing floating point numbers, we normally talk about the IEEE floating point notation. IEEE is a standards organization, and they have provided two representations, one for representing single precision numbers and another for representing double precision numbers. Okay. Both have an implied base of 2, which means we are dealing with binary numbers again. Okay. So in the single precision representation, very similar to what we saw earlier, but with a slight difference, as you can see here. So what we do in this 32-bit single precision representation is that we use 23 bits for the mantissa, 8 bits for the exponent, okay, and this 8 bits are in the excess 127 representation. Okay. So, when you say 23 bits for the mantissa, 8 bits for exponent, obviously there is 1 bit for the sign bit that we will use. So, 23 bit for mantissa, 8 bit for exponent, 1 bit for the sign bit. And this 8 bit exponent, again remember we use the excess notation so that all the numbers will be converted to positive numbers. Minimum number that we can represent with 8 bit exponent in the normal 2's complement will be minus 127 to plus 128. So, this minus 127 now, if you put it in excess 127 representation will become 0. Okay. So, that is what we do here. So, we use a excess 127 representation for the single precision number. Now, double precision, now the idea of using a double precision basically is that you are able to represent larger numbers, okay, because you are providing larger number of bits to represent, which means you are able to represent things with better precision. So, which is why it is called as a double precision number. So, with this what we do here is we use 64 bits for the entire representation. So, 32 bits in the previous case, double, so it uses 64 bits. Out of this 52 bits is used for the mantissa and 11 bits is used in the exponent, okay. And since we are using 11 bit representation, remember this can go from 2 to the power of minus 1023. So, we use an excess 1023 representation, okay. So, this is how we do it. So, 52 plus 11 will give 63 plus of course 1 bit for the sign bit. So, 1 sign bit exponent is 8 or 11 depending on whether it is a single precision or a double precision representation, and the mantissa is 23 or 52 depending on whether it is single precision or double precision. So, single precision is 1, 8, 23, double precision will be 1, 11, 52. These are two standards that we use for single precision and double precision representations as specified by the IEEE notation. Okay. There are a few other optimizations as such which are done in this representation. Okay. So, what we can call as the peculiarities of this IEEE notation. So, we will just take a quick look at that. In this IEEE notation, the assumption is that the numbers will always be represented in a normalized form. Okay. This is to maximize the use of the available mantissa digits, that we have already seen why we do normalization. Okay. Now, what the IEEE notation does is does one more optimization on this, which is that in base 2 representation, this will imply that the MSB of the mantissa is always equal to 1, okay, because if when you normalize it, so we said that the most significant bit will become equal to 1. So, the idea that is used here is since the MSB will always be 1, okay, do I really need to store that 1 value in my mantissa bits as such? So, I can also treat that as a implied number and start representing only from the next bit onwards. So, you normalize the number, you will get 0.1011 something, let us say. So, what we will represent actually is not 0.1011 something, but you will leave that 1 out and represent it as 0.011 something, but assume that the actual number is 0.1011 something. That is, if I have 23 bits available to me, okay, out of the 23 bits, if I had represented it using normalized number, I would have represented as 0.1 something, which will be the 24 bits. Now, I am saying this 1 I will not represent, which means out of the 24 bits I can accommodate 1 more bit. So, I am actually representing a 25 bit number using the 24 bits available to me and treating that 1 extra bit, that first bit that I have, since it is always normalized, will always be a 1. So, we call that it is an implied again representation that is used over here. You do not store the MSB, but IEEE notation always assumes that all numbers are normalized and that the MSB is a 1. So, the actual MSB of the number in the IEEE notation need not be a 1, it can be either a 0 or a 1, because remember once you normalize it, the first most significant bit 1 is implied, it is stored separately, means stored separately in the sense you know that it is always a 1. So, you just keep it as it is. So, only from the next bit onwards we need to store, that can be a 0 or a 1. So, what is actually stored in the 24 bits may start with a 0 or a 1. So, that is, but you remember it is still a normalized number with a 1 that you will add when you are actually dealing with the numbers, okay, that is what we do. So, with this representation in the IEEE notation as such, you can write it like this. It is normally specified this plus or minus, it is 1 point mantissa into 2 to the power of e minus 127. Okay, this is the actual value of the number that can be represented using the single precision notation. Okay, so this is how the numbers are actually represented. So, what we mean by saying it like this is e minus 127 because you would have represented your e value will be in a excess 127 representation. So, the value you have to subtract a 127 from that to get the original value, and this 1 point m we are saying because your mantissa value here, remember this, right. So, this we have, this was a normalized number and this we have taken this first most significant bit out. Okay. So, that 1 is again a implied value. So, this M will represent the rest of the bits that you have here. And the way IEEE notation deals with that hidden 1 that we are talking about is that it takes it as the integer part of the mantissa. So, now we are no longer representing as a 0.1 something, instead you are normalized it by shifting that 1 also to the left. So, it becomes 1 point something and the rest of your exponent is adjusted accordingly. So, note that therefore, we use XS 127 and XS 1023 representation and not 128 or 1024, which should have been used. Okay. So, we use XS 127 and XS 1023 as the value for the exponent. So, now you can see what the actual exponent fields will be in the IEEE representation. So, minus 126 to 127 will be the representation, not minus 127 to 128. The reason for this is that, remember, you are right already treating the number as 1 point something, and similarly in double precision representation it is minus 1022 to 1023 and not minus 1023 to 1024, because again same reason, we have shifted that 1 already to the left. So, accordingly we would have changed the exponent from 1023 to 1022, 1024 to 1023. So, that is the reason for this. Okay. So, these are certain optimizations which are done in the IEEE representation. And what IEEE standard does with the other two fields, that is you can represent these two values, right, the actual values of 0 and 255, that is the ones which correspond to minus 127 and 128, those values are used to represent certain special conditions. So, if you have a value of 0, okay, in the exponent field, okay, it is used to indicate an exact 0, because remember, if I want to have actual value 0 to be represented, I need a special representation for that in this floating point representation. So, we use the value of exponent value being 0 as an exact 0 representation, and similarly if the exponent value is 255, we use that to indicate infinity. Okay. Otherwise, the maximum value you use that to indicate infinity and use the 0 value to indicate a value of exact 0. Okay. These are two special numbers that are represented in this format. Okay. Now, coming to the floating point arithmetic, it is very simple. We are already familiar with this with respect to decimal. So, we will take an example from decimal and understand how the same thing is done with binary numbers as well. So, if you take decimal addition, look at what do we do, 3.1415 into 10 power 8 plus 1.19 into 10 power 6. So, what would you do? You would normalize the numbers, or you would equalize the exponents of the two numbers before you can add the numbers. Okay. So, what would I do? I have 10 power 8 here, so I can bring this also to 10 power 8. So, in which case I will write this number as 0.0119 into 10 to the power of 8. Okay, I will do a right shift and accordingly add 2 to the 2 digits shift right. So, this will become 10 power 8, or in fact I should look at it the other way around. If I want to make this 10 power 8, I will have to shift this right by 2 digits. So, it will become 0.0119 into 10 power 8. Now, I can add the two mantissas and write the answer as 3.1534 into 10 to the power of 8. Okay. So, what is to be remembered here, when we do addition or subtraction, the exponents have to be equal before you can add or subtract the mantissas. So, making the exponents equal is an important aspect before you do the addition or subtraction. Now, coming to multiplication. So, what do we do in multiplication? It is a simpler operation. You multiply the mantissas, the same two numbers we are multiplying. So, the answer will be multiply the mantissas and the exponents have to be added. Okay. So, this is what we need to do. Same thing we have to do in the case of binary numbers as well. But when we deal with IEEE numbers, we will see if any adjustments need to be done. And with respect to division, again remember what do we do for division? Simple, right? We divide this number by this number, divide the two mantissas and you will subtract the exponent of the divisor from the exponent of the dividend. Okay. So, this will become into 10 to the power of 8 minus 6. Same idea to be used here as well. Okay. Now, the only problem we have to look at is, in the case of floating point arithmetic in IEEE representation, we are using this concept of a biased exponent. So, when we use a biased exponent, okay, let us look at what happens when you do this multiplication. So, you have some a into 10 to the power of x plus p, because x would actually have been represented as x plus p, and b will be into 10 to the power of y plus p, because this again is an excess representation. Okay. When I multiply these two, a and b I will multiply the two mantissas, but look at what is happening to the exponent. Exponent, when I add these two, I will get x plus p plus y plus p, which will actually be x plus y plus 2p. Now, if I want my answer back in the excess representation, I should actually get x plus y plus p, because there is only one p that needs to be added. But what I get here is x plus y plus 2p. So, I will need to therefore do an adjustment there. So, I need to handle this bias when I do floating point arithmetic, which is that when I do this kind of a multiplication, I will need to subtract a p from this sum of the two exponents before I can take the value as the answer. Okay. Similarly, when you do division, you will see that you will do x plus p minus y minus p, it will only give you x minus y. So, to bring it back into the x's notation, you will have to add a p to the exponents. So, this is the only adjustment that we need to do when we do the floating point multiplication and division. Otherwise, whatever we are doing in decimal, the same thing needs to be done for floating point arithmetic as well. So, for addition subtraction, this is the following steps that we normally follow. So, you will choose the number with the smaller exponent and shift its mantissa to the right until the exponents of both the numbers are equal. We do this because we know we have to equalize the exponents for addition and subtraction. Okay. So, then depending on whether it is an add or a subtract, you will add or subtract the mantissas, you determine the sign of the result, and this is an important step. Now, you will normalize the result if necessary, okay, and truncate or round it to the number of mantissa bits. Okay, a truncation or round is done because you have only a limited number of mantissa bits that are available. Okay. So, this is what you do for addition or subtraction. For multiplication, what do? You add the exponents and then you will have to subtract the bias, because remember we got the 2p. So, we need to remove 1p from that. So, you will subtract the bias. You multiply the mantissas, determine the sign of the result, and again you will normalize the result if necessary and the truncate or round the mantissa of the result. That will give you multiplication. Division, again subtract the exponents. Remember you have to add the bias here, add the bias, and the mantissa similarly divide the mantissas and determine the sign of the result and normalize the result if necessary. Again truncate or round the mantissa of the result. Now, the truncate or round, as we do in the case of decimal, we could do it in the case of binary as well. There are some specific round off techniques sometimes which are used that will vary from standard to standard. This is basically what we have in terms of the floating point arithmetic. Typical hardware that you have for doing floating point arithmetic therefore will look like this. So, whatever we talked about now is what you will see over here. So, your sign exponent fraction will be there, and then this is for an addition. For an addition, remember we will have to compare the exponents and do a shifting of the mantissas based on that. You do a shift operation and then the actual addition of the mantissas whatever will take place, and then you will do a normalized step and then rounding if necessary, and then to find the final answer. Okay. So, similar thing is used for both for subtraction as well, and we can see that multiplication division again will use some similar hardware. Okay. So, to summarize, we have looked at we have tried to understand how things can be done with floating point representation. We had already seen range of floating point numbers, mantissa and exponent. We also saw the IEEE notation this time for representing numbers. So, we saw how the excess notation is used for the exponent. We looked at how normalization is done, and we looked at these 4 different operations of addition, subtraction, multiplication and division as done on floating point numbers. So, the exercises for you to try out today's to understand today's topic is very simple. Just take these two numbers, you normalize these two binary numbers. You have a number here 0.00011101 into 2 to the power of 21, and the other number I am giving here is 0.1010111 into 2 to the power of 23. Okay, these are two numbers. You can try to normalize these two numbers. You can normalize it in the 32-bit representation or also in the IEEE representation, and then perform addition, subtraction, multiplication and division on these two numbers. So, with this you should be able to understand floating point numbers. Thank you.